Hi everybody, this is the Algebra 2 lesson on section 2.2.1. The question is, how can I transform any graph? And we are going to be transforming other parent graphs. All right, so within this lesson, what I want to do is I want to go through a review of the parabola and graphing form for a parabola. And then what we're going to do is we're going to graph other functions. Now, normally what I would do would be to take all the functions and divide them up between groups and have you really focus on one and then make a poster and then come around and look at everyone's. But I can't do that because you know what? We're in a virtual world and we just can't do that. So what I want to review here is graphing form for a parabola. So this is for a quadratic function. All right, y equals, it was a times the quantity x minus h squared plus k. If you do not have this in your notes by now, you should. I've done it a lot of times. The a, that is your vertical stretch or compression or reflection over the x-axis. H is your horizontal shift. K is your vertical shift. What we're going to do is we're going to take other parent graphs and we are going to transform those as well. All right? But the thing is, we need to know what those shapes are first. What happens is those have a very direct relationship with the graphing form for that. All right? So I'm going to kind of go through, I'm going to go through the CPM lessons and I am going to graph the ones that the parent graph. So hopefully you do have some graph paper. All right? So here we go. First one is y equals x cubed. This is what we call the cubic function. All right, now I'm going to come up with a table for this. All right, and I think what I'll do is that as I go through, I'll do the graphing form for everything as I go through, and I'll keep going on this sheet of paper, okay? So you'll have graphing form. All right, so the question would be, okay, can I cube any x in the world? Yes, I can. I can cube negatives, I can cube positives, and I can cube 0. So I'm going to go -3 to 3. That's just the way I do things. Yeah, when you get as old as me, you just kind of keep doing things that way. Cubing x's, -3 cubed. -3 times -3 times -3 is, -3 times -3 is 9, 9 times -3, -27. Okay, -2 times -2 times -2, -2 times -2 is 4, 4 times -2 is -8. -1 cubed, -1 times -1 times -1, -1 times -1 is 1, times -1 is -1. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 squared is 20, or cubed is 27. Now, obviously not getting the -27 and the 27 on here because they only go up to 10, but I can get 0, 0, 1, 1, 2, 8, -1, -1, and 2, -8. Okay, the other thing that I'm going to have you guys do is, you know that in a quadratic, so I'll actually do a quadratic as well. Which is the parabola. This was y equals x squared. -3, -2, -1, 0, 1, 2, and 3. Here we go. -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. We know that origin started 0, 0, and we go up 1, then 4, and then 9 on a parent graph for a parabola, right? And then we'll do this. Needs to be smooth. All right. So within those, we have these locator points. They're the things that are the most important. Okay, the vertex is the most important because if I can move this, all the other points fall into place according to that. Same thing here. We're going to start your locator. All the circles we have, you guys, are going to be our locator points. Those are the special points that if we move just that point, we should be able to get all the graphs to fall into place, okay? Or all the other points on the graph to fall into place. All right? So, here is my thing here, you guys. Okay, this is what I got. In this one, I am going to list what the A, the H, and the K go, and then I'll have graphing form. And this should be actually graphing form if I can find my black pen. Review. This should be graphing form for a quadratic. Okay, A, if it's less than 0, this is a reflection over the x-axis. This is kind of small, but we've done this before. A's that are less than 1 and greater than 0, this is going to be a vertical compression. A's that are greater than 1, this would be a vertical stretch. H, this is our horizontal shift. And K, this is my vertical shift. All right. Graphing form for a cubic function, that's what we just did. All right, you guys, this is the thing that I really like about it. If I change this 2 to a 3, I have a cubic function. And guess what? I have graphing form. Y equals A times the quantity X minus H cubed plus K. The A, the H, and the K do the exact same thing in a cubic as it does in a quadratic. All right? Okay, so let's just describe some transformations. And if we have time, I'll graph one of them. So y equals, let's say I have y equals negative 3 times x minus 1 cubed. What does that do? Well, the negative is going to reflex over the x-axis. The 3 is going to have a vertical stretch, and it's going to go down because it's flipping. And the 1 is going to move it to the right 1. So what we would do is we would picture this thing moving it to the right 1. We're going to reflect it over the x-axis, so that means everything up will be down. And then we're going to stretch those points away from the middle. All right, so that is what that one is. That's my cubic function, and that's how we'll do all of them. We have a lot of functions to do. But important is that locator point. All right, next one is the hyperbolic function. Gosh, they just really go for it. Hyperbolic function. This is y equals 1 over x. Okay, so the question is, can I divide by any number in the world? Can x be anything? And the answer is no, it can't. It can't be 0, right? You can't divide by 0. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. I think you can still see there. Yep. All right. 1 over negative 3 is negative 1/3. 1 over negative 2 is negative 1/2. 1 over negative 1 is negative 1. You cannot take 1 over 0. 1 over 1 is 1. 1 over 2 is a half. 1 over 3 is 1/3. So here we go. We are not going to have any points. There's my wonderful highlighter. I'm not going to have any points at 0, so there's nothing here. Okay, and I'm also going to tell you guys, we'll get to horizontal asymptotes later. There will not be any points on the x-axis either. Okay, there is what we call a horizontal asymptote there. So a point at negative 1, negative 1, negative 2, negative 1/2. So obviously we're doing this, and then it's going to shift down. And we've had these graphs before. All right, so that is it. Okay. Now, for a hyperbolic function, you guys, what happens is that your vertical stretch, or I'm sorry, your vertical shift or horizontal shift are going to be moving your asymptotes. We're going to move those. Okay, so that's what that means. All right, so we did this one. Next one. Graphing form for a hyperbolic. We don't graph too many of these in the beginning. It's going to be y equals. Okay, there's a couple ways to do this. It could be a times 1 over x minus h, then plus k. You may see it as y equals a over x minus h, and then plus k on the outside. That happens sometimes, but that is how that one works. Okay, so if I want to describe my transformations, if I had something like y equals 1 over x plus 3 minus 4, okay, we would picture this thing right here. It would be shifted. This 3 is with the x, so it would move to the left 3 and then down 4. So we would take these asymptotes, move them to the left 3, down 4, and then those curves would go with it. All right, that's a hyperbolic function. Next, it looks like they have a square root function. So the question is, can you take the square root of anything? And the answer is no. You cannot take the square root of negative numbers. I also like to, at times, say, okay, are there any nice numbers I can take square roots of? Because I think that's going to be way easier. So what's the smallest number I can take the square root of? It's 0. What's the square root of 0? It's 0. What's the square root of 1? 1. Square root of 2, can't find that easily. 3, not easy. 4, yep, square root of 4 is 2. Square root of 5, 6, 7, 8, those are nasty, but 9 is 3. So this guy's going to start at 0, 0, 1, 1, 4, 2, 9, 3. There it is, you guys. That is my square root function. Ooh, and I forgot to circle my locator. The locator here is at the origin. Okay, this one's weird because the locator is actually the intersection of your asymptotes. All right, so that's kind of interesting right there. Again, I don't do too many of those. So let's see what we got here in this one. Okay, so my graphing form. Okay, this one's kind of closer to the other one. Okay, hyperbolic's weird. But if this was my parabola, you guys, for the cubic, I just changed this to a 3. For my hyperbolic, I would just get rid of this and put a 1 on top. For my square root, I'd get rid of this and just put a square root over it. That's it. Okay, so graphing form for a square root function is next. All right, it's going to be y equals, we're going to have a times the square root of x minus h plus k. That's it. All right, so again, describe the transformations. Let's go with y equals 1/4 times the square root of x plus 2 minus 5. And what that's going to do. All right, so the 1/4 is out in the front. This is going to be a vertical compression. The 2 is going to move it to the left 2. And this is going to be down 5. All right. So, nothing new there. Okay, just because I don't like to waste a ton of paper, I'm going to flip this over. Next one. Oh, this is my favorite one, you guys, the absolute value function. I'm a big fan of the absolute value function. Y equals the absolute value of x. It is just like easy peasy. So easy, I love it. All right, so can I take the absolute value of any x in the world? You bet I can. So I'm going to go negative 3 to 3. Okay, the absolute value of negative 3 is 3. The absolute value of negative 2 is 2. The absolute value of negative 1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3 is 3. So we're going to start at 0, 0, 1, 1, 2, 2, 3, 3. And there we go. That's my parent function. Oop, I didn't go to 2, 2. Bad me. I went to 1, 1, not 2, 2, 3, 3. Here we go. All right. So there it is, my absolute value function. Locator point, the point that goes with everything else, or everything moves with, it's right there. Which makes sense. It's like the lowest point. Parabola is the lowest point. All right. I'll take this. Next is graphing form for a absolute value function. Okay. So essentially, you guys, we're back to this one. The parabola. Get rid of this and put those absolute value bars there and you got it. Y equals A times the absolute value of x minus h plus k. There it is. Describe the transformations. Y equals the opposite of x minus 2 minus 8. And again, I should have said this earlier. If I'm talking too fast, just press pause. I just got a lot of things to do. All right. We flex over the x-axis. 2 is going to move it to the right 2 because it's in the opposite direction. This would be down 8. Fantastic. Okay, the last one that we're going to do is what we call, okay, I'm going to actually give you graphing form for this. It is called the exponential function, which you guys have had before. Okay, and I'll give you graphing form in just a second, but it's y equals b to the x. Now, I have to have a b. B has to be greater than 1. I like to use 2. I could use 3. I could use 4. But it's anything with a b. B is your base. It has to be a number. So, graphing form for an exponential function. It's y equals, we're going to go with b raised to the x. Okay, b has to be some number, and I'm going to make it 2 in my example. But if there's a horizontal shift, it'd be with the x, so that'd be minus h. If there's an a in front, that would be my stretch or my compression or my reflection, plus k on the outside. There it is. All right? But I have to give you b. You can't just graph something without a b. It's just not going to work, you guys. All right, so let's do that. I'm going to graph. And I'll give you the locator for this one too. All right, so we have the exponential function. Y equals b to the x. We're going to graph y equals 2 to the x. All right, guys, can we raise powers that are negative? Yeah. Try it in your calculator. You totally can. I'm going to go negative 3 to 3. Okay, I like to do the easy ones first. Because in math, it's awesome. When you use a table, if you can establish a pattern in a table, you can use it. That's what I love about math. Okay, 1, 2, 3. These are my exponents on the 2. What's 2 to the first power? That would be 2. What's 2 squared? That would be 4. What's 2 cubed? I'm sorry, 2 squared. My bad. 2 cubed would be 8. All right, so let's go backwards here. What do I do to 8 to get 4? 4 to get 2. I'm dividing by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1 half. Half divided by 2 is 1 fourth. 1 fourth divided by 2 is 1 eighth. If I keep dividing by 2, guys, will I ever get to 0? No, you won't. All right, so here we go. We had 3, 8, like that one. 2, 4, 1, 2, 0, 0, 1, and then we went a half, a third, quarter. Here we go. All right, and then you're probably like, oh my gosh, Miss Henschel, there's nothing at 0, 0. I can't circle anything. No, it's because it's 0, 1. Okay, and that's because any base raised to the 0 power always equals 1. That is why. So much fun, right? Okay, so graphing form you have. All these things do the same thing, okay? So if I had something like, let's say we're going to describe the transformations, and we'll end it with this because you know what? I went a long way today. Describe the transformations. Actually, I'll finish off with one. Describe the transformations. Let's go with y equals 3 times 2 raised to the x plus 4 power. All right, now you have to keep in mind your base is 2. That is my parent function. All right, the 3 is going to give me a vertical stretch. The 4, the 2 does not do anything. That's my base. The 4 is going to move it to the left. 4. Great. So what I want to do, because I have graph paper to do it, why not do it? I want to graph one. Let's graph y equals 3 times the absolute value of x plus 5 minus 4. I like it. I could have done this in one of my other ones. I could have had a describing close to it. But because I love the absolute value, you guys, I am going to do one with the absolute value. All right, so here's what I would do first. I would graph the parent function. Is y equals the absolute value of x. If you don't want to make a table, you actually don't have to, because you know that the absolute value, just do like absolute value of x is. When x is 0, isn't your y 0? What's the absolute value of an x of 1? 1. Absolute value of x of 2? 2. Absolute value of x of 3? 3. Absolute value of negative 1? 1. Negative 2? 2. Negative 3? 3. That's exactly what I had before, you guys. There's my graph. Now, what do my transformations do? This is going to give me a vertical stretch. 5 is going to be left 5. And this is down 4. So if I can figure out where this goes, I can stretch it. Okay? So here we go. I'm going to move it to the left and then down. Left 5, down 4. 1, 2, 3, 4. There it is, right there. Now, here's what I'm going to do. My stretch is 3. Rather than going up 1 here, 1 times 3 is 3. So from here, I'm going to go up 1, 2, 3. Other side, 1, 2, 3, because they got to be the same. Here I went to the right 2 and up 2. Rather than going up 2, 2 times 3 is 6. So 2, 3, 4, 5, 6. And on the other side, 1, 2, 3, 4, 5, 6. And then finally, I went up 3 here. 3 times this 3 is 9. So go to the right 3. Up 9. So this was 6, 7, 8, 9. And this was 6, 7, 8, 9. There we go. That's my stretch of 3. Do you have to have the parent graph down? No. Is it super helpful? Of course it is, okay? So one of the things we're going to start to do whenever we get back to class is that I'm hoping to have a pear deck made for you where it's like matching and you're going to drag a star or something on top of a graph that matches. You should be able to match any graph with its function. All right? All right. Good luck.